already. So, but I can tell you the, averages, the information there. That's what we've been waiting for, and you'll get your results later tonight. So the midterm 3 average across all sections was 73.4%. All right, that's actually kind of where I thought it would be given, is this on? Yeah, given the types of questions that I saw. Our section was a 76.9%. Yes, we were the high. We were the high, very good. And to put this into perspective, last year, the average was an 81. And you might be thinking, oh, we did worse this year. Last year, there was the internet outage. The internet outage happened during midterm 3, 10, 15 minutes in, and then we couldn't get it restarted. So what ended up happening is we kind of rescheduled the midterm 3, and it ended up being a take-home exam. That was essentially open book. We didn't have it under Respondus lockdown browser. It was just, you take it in a 24-hour period. We assumed everyone would have their book and resources up, and that exam was an 81%. Yeah, but it was a different exam, so do mention that. So you guys had your closed book exam, and you are pretty close, so I think that's pretty good, right? So any questions about that? Okay. Okay, all right, so let's continue on with chapter 10. So we have 3 more chapters to cover, not too many days left, so we're moving like a freight train here. All right, so we left off talking about pressure, one of the only terms we haven't really talked about yet, measurements we've talked about yet, but it's very important with gases. So essentially with gases measured in pressure, we have a force over some type of area. That's where our atmospheric pressure comes. If we weigh all of the force coming from the particles, the weight of the particles on our heads, it's 14.7 pounds per square inch of our body is being pressed down with the air particles that make up our atmosphere. So these conversions, very important to memorize, okay? Oftentimes we're going to be converting pressure measurements to atmospheres, but a question can give you a pressure measurement in millimeters of mercury or torr, and so being able to convert to atmospheres is really important there when we get to the ideal gas law. So we did some measurements or some conversions here, and so just like dimensional analysis, we need to bring back out our calculators for this chapter. You can see that there. So how do we actually measure pressure? So you guys are done with in-person labs, but if you were, had your eye out for it, you might have seen this barometer in the balance room in the lab. Did anyone see this? Okay, when you did your gas lab, didn't your TA just give you the pressure? That's dumb. So before, when we used to do that lab, we'd make you actually measure the pressure using this barometer. So the thermometer is the blue liquid, the barometer is the red liquid. So it moves up and down based upon the small changes in atmospheric pressure in the room. So it's very, very close to 1 atmosphere if we measured it right now, but we would see small fluctuations from 1 atmosphere. So it's like on the Weather Channel when they say, oh, we're in a high pressure system, we're in a low pressure system. That just means we're deviating a little bit from 760 torr. So how we can measure a more simplistic barometer here is we have this container filled with mercury. Mercury has a really high density. It's a really high density liquid, and we have this inverted tube. So let me show you how we can measure pressure here. In this inverted tube, we have a vacuum on the inside. All right, so if you think about a vacuum, there's no particles, there's no gases. So does a vacuum exert any force or any pressure? No, it doesn't. A vacuum essentially means the absence of pressure. All right, so how a barometer works is on the outside here, there is atmospheric pressure pushing down on this pool of mercury. And because this vacuum is not exerting any force, we essentially need to equalize the force being pushed down on the atmospheric pressure with the actual weight of the mercury itself. So what these arrows are trying to show is that the weight of the mercury that is inside this tube is equal to the atmospheric pressure on the outside. So if we have any changes here, we will see a increase or decrease in or height of that column of mercury. And so that's where the unit millimeter of mercury comes from. It's literally like how long of the tube of mercury is being occupied there to equal your atmospheric pressure. So the question is, why do they use mercury? It's because mercury is really, really dense. So if we wanted to replace this apparatus with water, we would need like 34 feet of water in order to equalize the force of the weight of the water with atmospheric pressure. So it's just not reasonable for us to read, an instrument that's 34 feet high. It's easier to just use about a meter's worth of mercury to make that measurement. All right, so that whole idea is really important, that the atmospheric pressure on the outside of the tube has to equal the weight of the mercury inside the tube, because that's essentially what helps us predict how gas samples change. That the force coming from inside your sample, all right, the force that gas exerts will always try to equalize with the force outside of pushing in on your sample, right? So the force on the surroundings always is equal with the force being exerted by the gas. And so sometimes small changes in either like volume or temperature will happen in order to make those two forces equal. All right. So with that in mind, hopefully you can visualize that it's like this arm wrestling match between gases, the pressure of gases and the pressure on the outside, or forces from the outside and inside happening. So let's look at with that in mind, all right, there's always equalizing in forces happening. Let's look at a different example of something that kind of looks like a barometer, but it's specific to gas samples, all right? So we can measure the pressure of a gas sample by comparing it with the atmospheric pressure. So I want to show you what this manometer looks like. So here we have a tube. Pressure is this tube is open on the end, so that means the atmospheric pressure is pushing down on this column of mercury. But we have this gas sample inside the tube that is exerting a pressure. So it's not a vacuum, it's an actual gas sample. All right, so based upon this picture, is the gas sample more or less than 1 atmosphere, or 760 millimeters of mercury? Is it more or less? Sometimes it's hard to see, so think about it. Which sample is winning? The gas sample or the atmosphere? Which one's winning? The atmosphere is winning. So does that mean the gas is more or less than exerting more or less pressure than the atmosphere? Less, yes, because it is not winning, all right? That essentially the force being exerted by the atmosphere is stronger, all right? And so that's why the column of mercury is pushing its way up to the gas sample. So we can say this, that the atmospheric pressure is greater than the gas sample. So if we made up a number, if we said this was like 2 centimeters, so 20 millimeters of mercury, and this is mercury, the thing in the tube, what would the pressure of the gas be? If the height of the difference in this mercury tube is 22 millimeters, what's the pressure of the gas? Is it 760 plus 20 or minus 20? Minus 20, so it would be 740 millimeters of mercury. So what you can think of here is essentially, in order for the two forces to be equal, all right, the pressure from the gas plus 20 millimeters of additional mercury is equal to 760 millimeters of mercury that is being pushed down from the external forces here, all right, because the external is winning and the gas is losing. So if we look at this picture, who's winning? Who's winning? The gas. So in this example, the pressure of the gas is exerting is greater than the atmospheric pressure. So let's make up a number. Let's say that the pressure difference or the height of our manometer is 1 centimeter, so that is 10 millimeters. So what is the pressure of the gas sample? 770, yes, because it is winning. It is applying more force here, able to push up an additional 10 millimeters of mercury on the other side. All right, so again, gas samples at the external versus the sample, always trying to equalize that force. And through the column of mercury that's being displaced, that's where that additional force can come from to make it equal. All right, okay, so we answered those questions. So which one exerts a pressure greater than 1 atm? So the answer is B, right? Yes. And you could see that you don't even actually have to calculate anything. You could just look at the diagrams and see, oh, the gas is, you know, pushing, is exerting a greater force than the atmosphere, right? Because of how the column of mercury is oriented, and you could get it that way conceptually as well. All right, so that is a manometer. So let's talk about different units and measurements that will be useful to us for solving calculations that we'll do this lecture and for this chapter. I'll point out that chapter 10, all right, chapter 10 is like the last chapter we need our calculators. Chapter 11 and 12 are very conceptual again, all right? So a little bit more math, but the math isn't too bad. As you can see, everything we've done this term is no harder than like algebra, right? Yeah, so it's just hard when it's in words. You know, when it's in words, that's the hard part. All right, so a lot of these we've already talked about before, these units. Volume, liters, milliliters. So knowing these conversions between liter, milliliter, and centimeter cubed is going to be useful here. So bring that back out of your back pocket. We're going to be talking about number of moles of gas. So we usually define this variable as N. So the idea of moles, and think about all the different ways we're able to calculate moles of substances, right? If we know the gram amount and the molar mass, we can get moles. If we know the molarity and volume, we can get moles. Lots of ways to get moles here. We also talk about temperature of gas samples. We'll always be using the unit of Kelvin. So it's useful for us to know the conversion here between Celsius and Kelvin temperatures, just because thermometers that we typically use are measured in Celsius, but we want to convert it to Kelvin before we put it into a equation. And then finally, pressure, the ones that we talked about, well, that's a mistake, we talked about earlier. And those different units. Oftentimes chemists are lazy and they don't want to say explicitly, okay, this is the temperature, this is the pressure of the sample. So sometimes we're lazy and we just say STP conditions. If a question states STP, it means standard temperature and pressure. And so what that just means, standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere. It's just the lazy way of saying it. So if we just say SPT conditions, then it just means these conditions, instead of actually saying the temperature and pressure. All right, so these variables are going to change in our named gas laws. All right, so that's what we're going to talk about now, and I'll do some demos. All right, so gases is a very ancient type of chemistry observation that happened in older times, where they were able to okay, my goggles are all messed up. Okay, great, okay, then I'll just use theirs. All right, that they were able to make small changes in gas samples and just observe what happened, all right? And so they would basically fix some variables. So if we're thinking about pressure, volume, temperature, they would fix some one variable and change another and see, okay, how does that variable, the other third variable change? So we're looking at pressure, volume, and temperature here. So what Boyle's law states is that at a constant temperature, the volume of a gas will vary inversely with the pressure exerted on it. So right now, what pressure is being exerted on us right now? 1 atmosphere, right. Okay, so 1 atmosphere, it's coming from, the atmosphere. I have a vacuum pump here that is able to reduce the pressure in a small environment. So in this bell jar, I can just locally reduce the pressure inside this jar. So I have a marshmallow man in here. Okay, does anyone know how a marshmallow is made? Has anyone made a marshmallow? Okay, so I will tell you what a marshmallow is. A marshmallow is, they take molten sugar, they add a little bit of gelatin in it to make it squishy, all right? So they heat it up, they heat up the solid sugar to make it molten, so a liquid, and then they whip the crap out of it, all right, with like a stand, I hope with a stand mixer, okay? So when you whip molten sugar, all right, and it starts to turn white, what's the purpose of whipping it? Yeah, to incorporate air, all right? So we're incorporating air, we're incorporating little bubbles into the marshmallow. So this marshmallow has tiny bubbles in it, all right, that it's encased with sugar. And so each of those bubbles right now, how much pressure is being exerted on it? 1 atmosphere. But if I turn on the vacuum pump and I reduce the pressure being exerted on those little bubbles, okay, we're gonna make the pressure go down. All right, that's being applied to the bubbles. So what would we expect to the volume of the bubbles? How would it change? They should expand, yes, and hopefully that's what happens. Okay, let's do it. Okay, so come on, little vacuum pump. I gotta make sure there's a good seal there. Okay, so look very carefully. Do you see he's expanding? Yes, he is. He is expanding. He'll expand to a certain point before the bubbles kind of lose their integrity, all right? So there he is, all big, because we reduced the pressure inside. And then I'm just gonna, there we go. Okay, so there's our marshmallow man. And so that, did you hear the whooshing sound? Okay, what do you think that whooshing sound was? All the air coming back in, yeah, because the point of this vacuum was I was removing the air, removing the pressure that was originally in here. And so then once I took this tube away, then all that air pressure then returned. Okay, very good. So that is Boyle's law. And so what I have in the box is the relationship, but oftentimes we can use it numerically to look at, okay, if we multiply the pressure and the volume at an initial state of your sample, it will equal the pressure and volume of its second state, its second condition, right? But it's the same sample. So when N, or the number of moles of gas, stays constant. All right, so next we will look at Charles' law. So note here, what is staying fixed? It's at a fixed pressure. The volume of a gas is proportional to its Kelvin temperature. And so remember Kelvin temperature here. So at a constant pressure. So that's the important part. Oops, the important part here, because that's this demo. I need my goggles. What pressure is being exerted on this balloon right now? 1 atmosphere, yes, 1 atmosphere. And so if I make changes to it right now, the external pressure on this balloon will still stay 1 atmosphere because it's not in the bell jar, all right? When we use the bell jar, we reduce the pressure, but because we're doing benchtop chemistry, okay, we're doing benchtop chemistry, the pressure is just staying the same. All right, so what I want to do is there's a certain number of moles of gas inside this balloon. It's exerting the same pressure to equalize the force with the external pressure, the 1 atmosphere. So what I'm gonna do, it's currently at room temperature. So what I'm gonna do is pour some liquid nitrogen over it. Oh crap, I forgot what the temperature of liquid nitrogen. It's like 77 Kelvin. I think it's 77 Kelvin, all right? Versus room temperature is like 298 Kelvin. So I'm gonna reduce the temperature of this balloon. So what do we think is going to happen based upon Charles' law? It should shrink, yes. It should shrink because we're cooling it down, right? Okay, so go. Okay, so there it is, all shrunk. All shrunk, okay. Okay, sometimes when we do this demo with kids, they get amazed. So I wanna show you the shrunken balloon and ask you a question. All right. Look how puny this balloon is. Is there still gas in here? There's still gas in here? Yeah, so when we do this demo for like children, they get amazed when it gets big again. They get amazed. Because they think when it gets small that the gas just magically disappeared, but it's not. All we're doing is utilizing Charles' law, because when I take it out of the liquid nitrogen, what am I doing? The temperature is going back up. So that's why the volume increases again. And then if I put it back into the liquid nitrogen, all right, you can make it small again. You can make it small again. See, and you can do this an infinite amount of times because until the balloon breaks or something, the N value, the number of moles of gas that's in this balloon is staying constant. All we're doing is changing the temperature and therefore the volume. So the idea here is what's making the balloon shrink? What's the temperature? Yes, but like what is actually doing the work of like making it smaller? It's the atmosphere. The atmosphere is pushing it because there's one atmosphere all the time, right? And so basically once you're removing the force from in the inside by cooling the sample down, the atmosphere just crushes the thing. Okay, so there we go. There's our balloon. Okay, do we understand Charles' law? Okay, good. All right, so the idea with Charles' law is we could, in theory, reduce the temperature so much that the volume of the sample could become zero. And so if the gas sample's volume becomes zero, essentially what you're doing is liquefying the sample. So that's where the idea of absolute zero comes from, where you reduce the temperature of a sample so much that it no longer occupies volume. So within Charles' law, basically a thought experiment, they did some calculations and saw that no matter what the sample was, if you use the calculations in Charles' law, if you reduced the temperature so much to make the volume zero, all of the lines actually converge at negative 273 Kelvin, which is absolute zero. That is 0 Kelvin, is negative 273 Celsius. And so that's the idea, the theoretical idea of what absolute zero is. Okay, it's just a theoretical number. There's really no instance where we've actually made something, made a condition absolute zero. We've gotten really close, but it's very, very difficult to get to absolute zero. All right, so there we go. All right, that is Charles' law. Okay, so the last, or I guess the third gas law here, named gas law, is Gay-Lussac's gas law that states that pressure is proportional to temperature when your volume stays constant. So that's the important thing here. This one, this gas law is very similar to Charles' law, but I like to think of this relationship in terms of a Simpsons episode, all right, where Homer is baking beans on the grill, but he doesn't take the beans out of the can. So we've fixed the volume, right, since they're baking in the can. So based upon Gay-Lussac's law, if we increase the temperature of the can, what happens to the pressure of the can? It increases, right? And so if you increase the temperature of the can so much that the pressure starts to build up, there's a certain point where the canister can no longer handle that pressure. And so I feel like when you see this situation, you automatically think it's funny because it's like, oh, that can's gonna explode. Because we already understand the concept of Gay-Lussac's law, that temperature and pressure are proportional to one another. And that's what Apu thinks as well, because he gets a garbage can lid to protect himself, because he knows that that can is going to explode from being overpressurized. Right, so you do know that relationship. Okay, so good news is that you don't need to actually know all of these gas laws separately. We can actually just combine them all. Okay, we can combine them all, and basically Boyle's and Charles' law is enough to get us to the combined gas law. The combined gas law combines the terms of temperature, pressure, and volume all into one equation. So we use the combined gas law when it's the same gas sample that's just changing conditions. All right, so like when we think of like a can of beans, okay, it's the same amount of stuff on the inside of the inside of the can when we heat it up. Same thing with our balloon here. The number of moles of gas inside this balloon stays constant. All we're doing is changing the conditions of it. Even the little bubbles of like sugary goodness in our marshmallow, the N value, the number of moles, is staying constant. So we can combine all of our gas laws into P1 times V1 over T1 equals P2 V2 over T2, where The subscript 1s just describe condition 1, your initial conditions, and the 2s represent your like final conditions here. So how we use this equation is temperature always needs to be in Kelvin. It has to be in Kelvin. But we can be a little bit more lazy with pressure and volume. The pressure units just need to match. It doesn't matter if it's an ATM or millimeters of mercury. We just need to make sure that P1 and P2 match their pressure units. Same thing with volume. It doesn't matter if it's liters or milliliters. They just need to match on each side. And so what's great about the combined gas law is based upon the question, if any one of those variables is constant. So if I say, okay, this change happens under constant pressure, then the pressure term stays, basically falls out of the equation. Because if pressure stays constant and if we have the same number on both sides, you can just cancel it out of the equation. So if anything stays constant, it just falls out. So let's do a calculation. All right. So I'm going to just write the combined gas law and think about, okay, what pieces of information is given and what are we trying to calculate? So here I have at constant pressure of this atmosphere, we have a sample of methane, and it occupies this much volume at this temperature. What volume does the sample occupy at this temperature? So I like to go through the pieces of information and label, you know, what is P1, what is P2, like, etc. So here it says constant pressure and it gives the pressure. We actually don't even need to use that piece of information because since pressure is staying constant, it falls out of the equation. Okay, so what about 8.32 liters? What variable is that? It's a volume, but which volume? It's V1. I like to just call that the initial conditions because it's stated first. So V1 has a temperature that's related to it. So that is also T1. So temperature for the initial conditions. 420 Kelvin, what variable is that? T2. And then what is the question actually asking for? What variable? It's asking for V2. So at this point, it is just plug and chug. All right, so V1, 8.32 liters over T2 is 350 Kelvin. So it's already in Kelvin for you because I'm so nice. Over V2, that is what we are calculating here. And then T2 is given there at the end, 420 Kelvin. And so if you solve for V2, so 8.32 over 350 times 420, you get this answer. So I already have it. So basically 10 liters. All right. So 10 liters. We see that the volume increases because the temperature increases. So which law is that? Which law is that? Do you remember? It's like on the previous slide. Which law states that temperature and volume do stuff? Gay-Luz temperature and volume? No, that's this one. So what was this one? Yeah, this one, the one with the balloon and the liquid nitrogen, and we make it small, big, that was Charles' law. That's temperature and volume. So this example is demonstrating Charles' law. Yes, all right, let's look at the next one. So this is Charles, okay. We have a 30-gram sample of argon in a 2-liter flask at this pressure and temperature. At what temperature will the gas display a pressure of 10 atm if it's pumped into a 5-liter tank? Okay, so they give us the amount of sample. It looks like here they give us a volume, all right? And it looks like the volume's changing. So I'm gonna call 2 liters V1. I'm gonna call the 5 liters V2. 8.6 atm, that sounds like P1 to me. And 0 degrees Celsius, that sounds like T1, but I'm going to change it to Kelvin there, all right? So I have P1, V1, and T1, and it looks like we are trying to calculate our T2 temperature given this new pressure, 10 atm into a 5-liter tank. So 10 atm sounds like P2 to me, and then we are given the pressure and volume at that second condition. So it looks like we have 5 different variables and 1 unknown. So we can just go ahead and plug those in and solve for the T2 temperature there. So it looks like we didn't have to use that 30 grams of sample at all. And because the whole idea is that it's the same sample changing its conditions. So we don't actually need to know N in this case because we know N is staying constant. All right, and so let's put those numbers in. So we got P1, so 8.60 ATM. Volume is 2 liters over the temperature, initial, so 273 Kelvin, equals the new pressure, so 10 ATM. So good, the pressures units match. We have the new volume, so 5.00 liters over that T2 temperature. And so that's what we're solving for here. When you solve for T2, so what I would do is move the temperature over here on the other side. So I would do 10 times 5 times 273 divided by these two numbers. That's how I would do it. What's the unit of temperature when you solve for this? It will be in Kelvin, because remember, temperature units must be in Kelvin. Pressure units always match. Volume units always match. So, oh yeah, the answer is right there. So the temperature in Kelvin that you should get is 790 Kelvin. And then if you convert that to Celsius, about 520. Is that what people got? Is that what people got? Okay, so that's just plug and chug. But you need to be cognizant of, small unit conversions you need to do to make sure that the units match and temperature is in Kelvin there. Okay, so with all of those gas laws, Boyle's, Charles, Gay-Lussac's, the idea there was, okay, the number of moles of sample stayed constant. Oh, and I guess for this previous question, all right, in this previous question, I forgot to mention, nothing stays constant. Nothing stays constant, which is just fine. It's fine because we know all the variables in the combined gas law. Really, the only term that's staying constant is N here, the number of moles of gas sample. We're just changing its pressure, volume, temperature conditions. Okay, so Boyle's, Charles, Gay-Lussac's, those talk about N staying constant, the sample just changing its conditions. So now we're going to introduce Avogadro's law that says, okay, well, what if the number of moles of samples of gas does change? How do the numbers change? So Avogadro's law just says that if you have more gas, the sample is bigger. All right, the volume is bigger. All right, so the more moles of gas you have in, like, let's say a balloon, okay? All right, this has a certain number of moles of gas. How could I add more moles of gas into this? I could take the gas inside my lungs and blow into it to make it bigger, right? So if I blow into this balloon, I'm adding more gas particles, okay? I'm increasing N, but our intuition says when I blow into this balloon, the volume also gets bigger. And that's what Avogadro's law says here. All right, so we're no longer going to talk about just proportions anymore because we're adding this idea of moles. So lots of different things can change the volume of a sample. Volume is inversely proportional to pressure. It's proportional to temperature, and it's proportional to number of moles of gas in your sample. So we can combine all of those things together and say, okay, these are all the things that volume is proportional to. If we move volume to the other side, we can say that pressure times volume over the number of moles over temperature is equal to a constant. And this is how we get the ideal gas law, because that constant is the gas law constant. That's what we call it. We give it the variable R. Is our gas law constant. So this is our ideal gas law equation. So this is basically the second equation I've introduced. The first one was the combined gas law. That's where your sample stays the same. You're just changing its condition. We use the ideal gas law when we want to calculate a certain number of moles of one sample. If we just want to understand the condition of one sample at one condition, we use the ideal gas law equation. Because if you squint a little bit, you can see that the ideal gas law equation actually is the combined gas law. They're really the same equation. All right. So with this equation, pressure, volume, temperature, those same units we always think about. And now this new term we think about is R, our gas law constant. If you Google gas law constant R, there's actually a ton of different numbers for R. They all just have different units. We've actually already talked about an R. Do you remember what R we've talked about before? Not bond, yes, that's radius, but sorry, capital R. Yeah, 8.314 joules per mole Kelvin. Didn't we talk about that R before? Yeah, that's a different R, all right? That's a different, actually it's a different unit of R. It's the same R. They're actually the same number, just with different units. So again, if you Google gas law constant, you will find like 80 different iterations of R, but it's easiest to just memorize this one. If you memorize this one, where R is equal to 0.08206 liter ATM mole Kelvin, it'll be really useful to you, all right, to use in our gas law equation. You can use this R as long as pressure is in ATM, as long as volume is in liters, and as long as temperature is in Kelvin and N is in moles. We know how to convert basically any temperature, pressure, volume unit into these things. So making these smaller conversions is easier than memorizing a bunch of different R's. Does that make sense? So just if you use this R, you need to make sure that when you plug in these things, pressure is in ATM, volume is in liters, temperature is in Kelvin, and N is in moles. Those are the big ideas there. And it basically tells you it in the unit. So as long as you can see the units here, we need them to cancel appropriately. These are the units we need to use. Okay, so let's talk about the ideal gas law and what it tells us. Okay, so let's calculate what is the volume of a container if it contains 1 mole of gas. So what variable is that? N. Has an internal pressure of 1 atm, so that's pressure, and it's already an atm, and temperature of 0 degrees Kelvin, so 730 Kelvin, that's our temperature. So we want to know the volume. So we're going to use our ideal gas law equation because we're describing a sample at one condition. See how it's not changing? It's not changing, so we don't use the combined gas law. So I've rearranged our Pivner equation to isolate volume here. So I'm just going to plug in those numbers. 1 mole times R 0.08206 liter ATM mole Kelvin times temperature is 273 Kelvin, and then over pressure, so 1 ATM. All right, and that's also, this is also standard temperature conditions, standard temperature and pressure conditions, because it's 0 Celsius and 1 atmosphere. So it means the same thing. So when we calculate that, what volume do we get? 22.4 liters. So this equation is saying that 1 mole of gas at standard temperature conditions, so 0 degrees Celsius, 1 atmosphere of pressure. So like on Earth at just 0 degrees, that 1 mole of gas will occupy 22.4 liters. It's about like this much. It's about this much. All right. So if we have 1 mole of helium, that's what this is trying to say right here. The mass of the gas is 4 grams because 1 mole of helium weighs how much? 1 mole of helium gas weighs how much? 4 grams. Where'd you get that number? Off the periodic table. It has a volume of 22.4 liters. How many moles of nitrogen gas are in here? Based upon the number, the mass of the gas. Remember, it's N2 gas. It's N2 gas. So 1 mole of N2 gas weighs 28 grams. So basically all of these balloons contain 1 mole of gas. So that's what I'm trying to show you. So if we calculated the volume of all of these samples, they will all be 22.4 liters because all of them contain 1 mole of gas. They all contain 1 mole of gas, and that's what this graph is trying to show you up here in the corner. If you look closely, we have 1 mole of all of these different gases. Hydrogen gas, helium, nitrogen, ammonia, chlorine, and ideal gas. You see all of them, as long as there's 1 mole of gas at standard temperature and pressure, all of them will be about 22.4, very, very close to 22.4 because of the ideal gas law equation, that it's the N value that matters here, the number of moles of gas in your actual sample. So let's look a little bit closer at this idea of helium, nitrogen, and in this case, it's methane. Okay, all of them have the same volume because all of them contain 1 mole of gas in that canister. All right, and they all have the same volume. They all are at SPT conditions here. But what is different about these samples is the mass of them, because they have different identities. They have different masses because they have different molar masses here. All right, so volume's the same, but the densities of these gases are the same. So let's remember what density is. It's the mass of the sample over the volume of the sample. So we already said that the volume of all of these samples, when they contain 1 mole at the same STP conditions, they all have the same volume. But what is different are the masses. So based upon this information and the things I've highlighted here, which sample it has the least amount of density, is the least dense? Helium, yes. So if we rank this in terms of density, helium is the least dense. Then what's next? The CH4 one, methane, because it's 6 grams per mole. All of these balloons have 1 mole of gas in it. And then finally, it would be nitrogen, right? And if we actually calculated these values for fun, helium has a density of about 1.8 grams per liter. If we compare that to the density of air, which is 1.3 liters, we can see that big mismatch in density is what causes helium to float. If we calculated the density of methane, it's about 0.71 grams per liter. Does methane in a balloon float? Yes, it does, because it is less dense. And then finally, diatomic nitrogen, if you calculate the density, is 1.25 grams per liter. Do you think diatomic nitrogen floats? Just barely, and it's actually the weight of the balloon is enough to make it sink. Yeah, because remember, you don't have like the gas sample not in anything, all right? So just the weight of the balloon will make it sink. So yeah, diatomic nitrogen is right on the cusp, but it does sink in air. Okay. So there we go. So the idea is that N is the same in all of them, so the volumes are the same as long as the conditions are the same. But what is different are the masses and therefore the densities. So let's actually do some calculations. So we have our PV equals nRT equation. So think about all the times we talked about N, moles. We talked about moles when converting gram amounts to mole amounts. How do we convert like grams of CO2 to moles of CO2? How do we do that? We need to use what piece of information? Molar mass, yeah, so that's no different there. That should be review. All right, that should be review. So just think about all the ways that we can get moles here. And now we just think about, okay, we need to identify the pressure, volume, and temperature and figure out which one we're solving for. So here it says consider 12 grams of helium. We place it in a rigid container. So to me, that sounds like volume. This container will explode if the pressure exceeds 20 atm. So that sounds like pressure to me. So this is asking what temperature in Celsius will the cylinder or the container explode? So I have pressure, I have volume, R is a constant. I'm trying to calculate temperature, but how do I get N? Yeah, I have to convert. I can use the gram amount, so I was mean and didn't give you N moles directly. Instead, I'm giving you gram amount, but if you know the molar mass, you can convert it to moles, and that will give you your N amount. So you got to just do a little bit of manipulation before you can plug and chug in PivNert. So let's start with that 12 grams of helium. Convert that to moles, so use the molar mass of helium. What is it? Yeah, 4-ish. It's 4.003 grams per mole. So the 4.003 goes where? On the top or the bottom? The bottom. 4.003 grams is 1 mole. And so 12 grams of helium gas is 2.9978 moles of helium. All right, I just like to keep an extra sig fig because I don't want to round too early. All right, so I just keep an extra digit. So that is my N value. And at this point, now it is plug and chug. Now it's plug and chug. Where we are solving for temperature, so it is PV over NR, so pressure, 20 ATM. Volume, 5 liters. N we just got is basically 3, but it's 2.9978 moles. And then R, our gas law constant, 0.08206 liter ATM mole Kelvin. And so if you look really carefully about the units here, you can see how all the units cancel super nicely. Liters cancel, ATM cancels, mole cancels. And so what we're left with is a Kelvin on the denominator under a denominator. So basically, if you calculate this, you will get your temperature in Kelvin. Yes, it's like a double flipperoo, one of those. All right, and so put all those values in your calculator and you get, oh, it's right there. The answer's right there. Okay, very good. It's like 400 something, but it's in Kelvin. So be very cognizant of what the question is asking. I ask for it in Celsius. So you're not quite done. Once you have that Kelvin temperature, you need to subtract 273 to get your Celsius temperature. Good? Okay, so that was like a plug and chug, but like a little extra step at the beginning. So let's do another one. Let's calculate the number of molecules in a deep breath of air, which has this volume at this temperature, so 37 Celsius. So the Kelvin temperature here will be something like 310 Kelvin, and has a pressure of 735 torr. So I can quickly calculate the ATM pressure because I know I'll need that for my ideal gas law. It's something like, so 735 torr over 760 torr is equal to 0.967 ATM. So that's my pressure. So if we go through this equation, we know pressure, we know volume, R is a constant, we know temperature. So it looks like we're calculating for N here. And so if you read the question, it's asking for molecules. So what piece of information did we learn about in chapter 3 that related moles and molecules? Avogadro's number. So in this example, we're just going to plug and chug first to get N. Once we have moles of gas, then we can use Avogadro's number to get our number of molecules. All right. Oh yeah, I have it there. So once we get moles of gas, N, we'll use Avogadro's number to get our gas molecule. So now it's just plug and chug. So N equals PV over RT. So pressure is 0.967 ATM. Volume is 2.25 liters. I guess that's how much your lungs can hold. And then finally, R 0.08206 liter ATM mole Kelvin times in temperature in the denominator as well, so 310 Kelvin. And so if we look carefully how the units cancel, Kelvin cancels, ATM cancels, liters cancel, and now we have a mole on the denominator in a denominator, so it's another switcheroo unit thing. And so we do have the mole unit come out here. And so we get, stick that into your calculator, N equals 0.0855 moles of gas. Is that my answer? No, that's just the number of the moles of gas within the ideal gas law equation. So in order to get to molecules, we just take it one step further using Avogadro's number. So 1 mole of anything is 6.022 times 10 to the 23 particles. And that's how we get this answer there. All right, so this question does say molecules. All right, so molecules, if we think about the molecules in our air, we have like CO2, oxygen, those are all molecules. But there could be some atoms in there too, because some elements, some things in our air are just elements like helium or argon, those types of things are atoms as well. So it's just all gas particles really within our breathing air. All of anything that's in the gas form would contribute to that N value. All right, so let's do one more. Oh no, a couple more here. Oh, a couple more. All right, so let's connect this to stoichiometry. Remember, we're talking about moles here. That new N term in PV equals nRT is going to get us a long way. Connect it back to stoichiometry. So here I'm telling you that 12 grams of sodium azide is placed into an airbag. This is the component in airbags at STP. What is the final volume of the airbag if all of the NaN3 decomposes? So our strategy here is we are given the reactant. But does the reactant, does that mole amount go into PV equals nRT? Why? Why not? It's a solid. So what's the only component here that would go into PV equals nRT? Nitrogen gas. So we need to figure out how many moles of nitrogen gas we have. So that's stoichiometry, because we're given sodium azide, but we want to figure out, okay, how many moles of N2 gas do I actually have? All right, so I'm going to start with 12 grams of sodium azide. I give you the molar mass, so I can figure out the number of moles of gas, or sorry, of the solid I have. So I'll even mention that this is the solid. So 65 grams is 1 mole of sodium azide. But that's not it, so I'll just calculate it here for you. That is 0.1846 moles of sodium azide. But we do not put that number in our ideal gas law equation because that is a solid. We want to calculate the moles of gas. So what do? We use the coefficient. So this is stoichiometry, where we're in moles, so we can get on the bus to go from sodium azide to nitrogen. So what number am I going to put on the bottom? What number? 2 moles of the sodium azide. And what goes up top? 3 moles of nitrogen. And so if you multiply that number by 3/2, you get that there are 0.2769 moles of, I have 3 minutes, of nitrogen gas. This is the number that goes into our PV equals nRT equation, right? But the question didn't give P or T. What is it? Oh, it's at STP. Very good. All right. So STP, remember, means 0 degrees Celsius, 1 ATM. All right. And so you can plug it into PV equals nRT. And in this case, we're solving for volume. And so when you stick that in there, volume ends up being, what is it? Oh, it's already right there. It's 6.21. I keep forgetting I put the answers there. All right. You can also use the trick here at STP, all gases, 1 mole of gas will always occupy 22.4 liters. So if you multiply that N value by 22.4, you'll get the same number. But it's the same number you'd get if you plug it into PivNert as well. All right, so we have 2 minutes. I just want to show you how to get these next 2 questions started. All right. Because I think the book does a poor job of talking about these 2 questions. So we can use the ideal gas law equation for 2 more applications. The first is determining the molar mass of a pure gas, and the second is determining the density of a gas, given a chemical formula. So they like to take the PivNert equation and rearrange some of the terms to come up with a new equation. I hate memorizing things. I hate it. So if we're trying to calculate the molar mass of something, remember, think about what the unit of molar mass is. Molar mass is grams per mole. So given all this information, does this problem give us how many grams of gas we have? If you look at the problem, yeah, it's right here. They give it to us. It's right there, all right? It's given in the equation. So how can we get moles of gas given all the rest of the information here? Yeah, you use PV equals nRT with all the rest of the information. All right, PV equals nRT. The book gives like a different equation to solve for it. I don't like to do that. I just like to look at the unit of like the thing we're trying to calculate. All right, okay, so the next one, and we'll do this in class on Monday, is, okay, let's determine the density of a gas. So same reason here. Think about what is the unit of density. It's grams per liter. All right, so the strategy here is always assume with the information given, they usually give you a formula, assume you have 1 mole of gas. So if we have 1 mole of gas, do we know how many grams of gas we have? If we have 1 mole of N2? Yeah, if we know the molar mass, how could we get liters of gas? If we have 1 mole, that's N, and then they have to give us our temperature and pressure, we can piv-nert again to get the denominator. So the top comes from molar mass, the bottom comes from piv-nert. So we'll do these examples. I just wanted to point out in the book, they give like confusing equations. You don't need to do that. We'll finish this on Monday. Oh, they're gonna release the scores at 7. At 7.